Why do we classify numbers? Why do we give them names like integers, irrational numbers, or negative numbers? For the same reason we classify anything. We want to make sure that everyone has an understanding of what specific numbers are called and what they mean. After all, there's a difference between 25 and negative 32 and 4 to the 6th power. In this Mometrics video, we'll provide an overview of numbers and their classifications. Numbers are our way of keeping order. We count the amount of money we have. We measure distance. We use percentages to indicate a sale. Numbers are an integral part of our everyday existence, whether they are whole numbers, rational numbers, or the first type of numbers we're going to look at, real numbers. A real number is any value of a continuous quantity that can represent distance on a number line. Essentially, it's any number you can think of. 50 is a real number. 1 billion is a very large real number. Real numbers encompass 3 classifications of numbers, which we'll talk about in a little bit. Whole numbers, rational numbers, and irrational numbers are all real numbers. Imaginary numbers are not real numbers. They are complex numbers that are written as a real number multiplied by an imaginary unit, I. For instance, the square root of -1 calculates as the imaginary number I, and the square root of -25 is 5i. Even though imaginary numbers aren't real numbers, they do have value. Electricians use imaginary numbers when working with currents and voltage. Imaginary numbers are also used in complex calculus computations. So just because these numbers are called imaginary doesn't mean they aren't useful. Whole numbers are numbers that we count with. 1, 2, 3, 4, and 5 are all whole numbers. So are -17 and 0. Whole numbers do not have fractions or decimals. All whole numbers are called integers. Integers can be positive or negative whole numbers. All integers and whole numbers are part of a bigger group called rational numbers. This group also includes fractions and decimals. That means that 3/5 and 7.25 are rational numbers. Rational numbers can also be positive or negative. Rational numbers have opposites, which are called irrational numbers. These numbers can't be written as a simple fraction. Pi is the most famous irrational number. We have a close approximation of how to calculate pi, but it's just a close approximation. Pi is renowned for going on and on forever. That's why it's an irrational number. You can't easily write it as a fraction. Natural numbers are those that are positive integers, although there is some debate as to whether natural numbers start at 0 or 1. Negative numbers are, well, exactly that. They are the numbers below 0. There are several other number classifications as well. Numbers are divided into even and odd numbers. If you can divide a number by 2, that number is even. So 24, 36, and 74 are all even numbers because if you divide them by 2, you get 12, 18, and 37. Even numbers always end with 0, 2, 4, 6, or 8. Odd numbers can't be divided by 2 and leave a whole number. Any odd number divided by 2 will leave a fraction. So 17 divided by 2 is 8.5. 23 divided by 2 is 11.5. All odd numbers will end in 1, 3, 5, 7, or 9. Numerators and denominators form fractions, which are comprised of 2 integers. The number on top is the numerator, the number on the bottom is the denominator. The numerator, the top number, shows how many parts we have. The denominator, the bottom number, shows how many parts make a whole. Let's say you have 6 apples and 3 of the apples get eaten. The number of apples you have left over would be displayed as 3/6. You would then divide 3, the top number, into 6, the bottom number, to determine the percentage of remaining apples. In this case, the number is 50%. Hey guys, welcome to this Symmetrics video on fractions. Fractions can be simple or complex. In this video, we'll cover different types of fractions and how to add fractions with different denominators. So, what is a fraction? A fraction is a part of a whole, which means a fraction can never be a whole number. Think of it like this. Our circle is divided into 8 equal pieces. Let's say 3 pieces were filled in. That means that 3/8 of our circle is filled in. The top number is called the numerator. And our bottom number is called the denominator. When saying fractions out loud, the denominator will usually be spoken as the ordinal version of the number. You would say 1/8 instead of 8, or 1/3 instead of 3. Let's take a look at a list of our denominators and see how we would say them. As you can see, there are a couple of exceptions. If our denominator is 2, you could say half instead of second. Or if our denominator is 4, you can say quarter instead of fourth. But either one is acceptable. Hopefully that helps you to understand how fractions are defined and also how to actually say them out loud. But there are different types of fractions. Let's take a look at those. First, we have a proper fraction. A proper fraction always has a numerator, which we looked at, that is smaller than the denominator. Our example that we used before, 3/8. So our numerator, 3, is smaller than our denominator, 8. Some other examples of proper fractions include 4/5. An improper fraction is the opposite of a proper fraction in that the numerator is larger than the denominator. So while 3/8 is a proper fraction, 8/3 is an improper fraction because the numerator is larger than our denominator. Improper fractions are always equal to or greater than 1. That means that 9/9 is an improper fraction since it's equal to 1. There are also mixed fractions, which contain a whole number and a proper fraction. Here's an example. Note that the whole number 2 is followed by the proper fraction 3/4. We also have equivalent fractions. Equivalent fractions are 2 different fractions that name the same number. For example, 6/8 and 3/4 look different, but they're the same. 3/4 is just a simplified or reduced version of 6/8. To simplify 6/8, you just divide the numerator and the denominator by 2 to get 3/4. Now that we know the different types of fractions, we can explore how to add them. If 2 fractions have the same denominator, adding is a breeze. You just add the numerators together, and that gives you the answer. For example, so notice what we did to get 3/4. All we had to do was add from our first fraction the 1 from our numerator, and from our second fraction the 2 from our numerator. Add them together to get 3, and we just bring over our 4 from the denominator. Simple. But what happens if the denominators are different? Well, in that case, you have to convert the denominators to be the same. So let's take a look at an example. can't really simplify 3/8 into anything that would easily add with 1/2, but we can do something with 1/2 that we could easily add with 3/8, and that's multiplying 2 by 4, which would give us 8. But whatever we do to our denominator, we also have to do to our numerator. So that would look like this. So our equation now becomes 3/8 plus 4/8 equals 7/8. Subtraction works the same way. If you're subtracting fractions with the same denominator, you can just subtract the top numbers, like in this example. So in this example, all we had to do was subtract our top numerators here, which gave us 2/4, which simplifies to 1/2. Simplifying numbers just makes them easier to work with. But if you're subtracting with a different denominator, you have to make the denominators match. For example, so in this example, 3/8 minus 1/4 is equal to x. We're kind of looking at a same issue like we did over here. We need our denominators to match. So we need to find out what can we do to make our denominators match. Well, in this case, we can multiply 4 times 2. But remember, we have to do the same thing that we do to the denominator, we must do to our numerator. So we can multiply it times 2, and then here's what we get. So once we multiply our second fraction here by 2, we get 3/8 minus 2/8, which gives us 1/8. So these problems were pretty easy because they had either the same denominator or were just really easy to convert. But let's look at one more equation that's a little trickier. So at first glance, it doesn't look like these numbers have much in common, such that we would be able to multiply or divide 4 by anything to get 7, or 7 by anything to get 4. So a lot of the times when you have problems like this, what you end up having to do is multiplying this fraction by the denominator of the other fraction. And likewise, we would multiply this fraction by the denominator of this fraction. So here's what that looks like. So after our multiplication, we end up getting a common denominator, which is 28. So now all we have to do is add our numerators together, which that gives us 45 over 28. And that's our answer. With this calculation, we found the least common denominator. The least common denominator is the smallest common number between denominators. Anytime you perform a calculation with different denominators, you must find the least common denominator to solve the problem.
Hi, welcome to this video on converting percentages to decimals and fractions. In this video, we'll show you some easy and not so easy methods for converting percentages. We use decimals in every part of our lives. You see decimals when dealing with money, measuring distance, measuring how much something weighs. There are decimals literally everywhere you look. But before we look at conversions, let's do a quick recap on percentages. A percent is any number that is a part of 100. The word percent literally means per 100. For instance, 25% is 25 of 100, and 64% is 64 of 100. But how do you convert the percentage into a decimal? Well, there are actually two ways you can do it. The first way is by using math. We've already established that percent means per 100. Using 25, 25% is really just 25 per 100. If you divide 25 by 100, you get 0.25, which is a decimal. But there's a much easier way to convert to a decimal, and it's something I like to call the math two-step. Just move the decimal in your percentage 2 places to the left. Let's use 25% as our example. 25 has 2 digits, the 2 and the 5. Our decimal is after the 5. Moving the decimal 2 places to the left gives us 0.25. As always, remember to remove the percent sign when you're done. Simple, right? But what if your percent number is over 100%? Maybe you have 125%. Well, the same applies. Move the decimal point 2 places to the left. You would move past the 5, the first point, and past the 2, the second point, and end with 1.25. Now that we've got that down, Let's look at converting percentages into fractions. This conversion has a few more steps. When you convert a percentage to a fraction, you first convert your percentage to a decimal, then divide that number by 1. Let's say with 25 again. 25% becomes 0.25. Now we divide that by 1. Next, for every number after the decimal point, multiply by 10. Since there are two numbers after the decimal in our example, we multiply 10 twice. If there were 4 numbers after the decimal, we would multiply 10 4 times. The multiplication factor is essential to remember. You're not adding 10 after each decimal point. You're multiplying. In this case, you'll multiply 10 times 10, which equals 100. So you'll multiply the top number and the bottom number by 100. 0.25 over 1 times 100 over 100 equals 25 over 100. Now, you have to simplify the fraction. You do that by finding the highest number that divides the top and bottom numbers equally. In this case, the answer is 25. 25 is the highest number that equally divides both 25 and 100. Here's how the equation looks. 25 over 100 divided by 25 over 25 equals 1 over 4. And there you have it. The answer is 1/4. That's our look at converting percentages to decimals and fractions, with a little simplification thrown in. By following this lesson, you should have a firm base for these calculations, which prove useful in many areas of our lives. Hi, and welcome to this video on ratios. Ratios are used all the time in many aspects of our lives. In this video, we'll review what ratios represent and how they should be interpreted. As mentioned, ratios are frequently used, but sometimes not fully understood. Simply put, ratios are an efficient way to compare numeric values of different categories. For example, let's say that you have a room of 20 people comprised of 12 women and 8 men. The two categories are men and women, so your ratios would look like this. The ratio of women to men is 12 to 8, and the ratio of men to women is 8 to 12. Note that ratios can be simplified by dividing both values by the common factor of 4, which will not change the meaning of the ratio. The simplified ratio still represents the relationship of the number of women to men, 3 to 2, and the number of men to women, 2 to 3. There are two ways that ratios can be written. This example uses a colon, but you could also use a division bar to form a fraction. 12 over 8 simplifies to 3 over 2. It is very important to note that the order of the categories matters when building a ratio. The first value is technically referred to as the antecedent, and the second value is referred to as the consequent. The antecedent is always compared to the consequent. Interpreting the ratio in context can sometimes be tricky, but becomes easier with practice. Let's look at some examples of ratios you might come across in day-to-day life. Cooking. You are making a batch of your mom's delicious salad dressing. The recipe calls for many ingredients, including 2 cups of extra virgin olive oil and 3 cloves of chopped garlic. In this case, the ratio of oil to cloves is 2 to 3, or 2 over 3, and the ratio of garlic to oil is 3 to 2, or 3 over 2. In cooking, you might hear this referred to as 2 parts oil, 3 parts garlic. This is because the units here are different, cloves versus cups. Shopping. Grocery store displays allow us to compare the value of products based on their unit cost. Many times, this is simply a quick ratio of cost to unit, with a unit being ounce, pound, etc. Suppose you're scanning the cereal aisle and narrow your choice down to your 2 favorites. You decide to be practical and base your decision purely on cost. Both have similar prices, but the volume of the packaging is different. Calculating a quick ratio of cost to unit for each box will reveal the better value. Brand A costs $5.79 and has a volume of 20.35 ounces. Dividing the price by the volume gives us the cost of the cereal per ounce, 28 cents. Brand B costs $6.39 and has a volume of 24.15 ounces. Dividing the price by the volume gives us 26 cents per ounce. Despite being a higher cost per package, choice B is a better value by unit price. This example was fairly straightforward because the volume of the cereal packages were both measured in ounces. Many times a unit conversion must be made before a unit price can be determined. For example, if we're trying to compare the unit cost of a pound of fresh broccoli to a package of frozen broccoli measured in ounces, we would need to know that 1 pound is equal to 16 ounces before we could calculate the unit cost ratio. In this case, the frozen broccoli would be the better value based on the smaller unit price per ounce. So, as you can see, ratios are common in our everyday lives, and you've probably been using them whether you have realized it or not.
Hello, and welcome to this video about proportions. In this video, we will explore what proportions are and what it means for quantities to be proportional, and mathematical and authentic applications of proportions. Before we get into proportions, we need to quickly review ratios. Recall that a ratio shows the relative sizes of two or more quantities. For example, in the alphabet, the ratio of vowels to consonants is 5/21. In a standard deck of cards, the ratio of face cards to total cards is 12/52. In all circles, the ratio of the circumference to the diameter is pi. There are many ways to represent ratios. Here, we'll mainly be working with the fractional representation. Ratios are not exactly fractions, but they can behave just like them. Now on to proportions. A proportion states that two ratios are equal. If I want to cook 1 cup of white rice, I would combine it with 2 cups of water. In other words, for every cup of rice, I need 2 cups of water. So the ratio of rice to water is 1/2. If I wanted to double the recipe, I would need 2 cups of rice and 4 cups of water. So 1/2 is equal to 2/4. These recipes are proportional because this is a true statement. In other words, their fractional forms are equivalent. On the other hand, the recipe for brown rice calls for every 1 cup of rice, 3 cups of water. The recipes for white rice and brown rice are not proportional because 1/2 does not equal 1/3. Let's look at using proportions to find quantities. In a standard deck of cards, the ratio of face cards to total cards is 12/52. Dealers in casinos often use 8 decks for blackjack. How many face cards would they use? In 8 decks, the ratio of face cards to total cards is still 12/52. So these quantities of cards are proportional. There would be 96 face cards. Let's look at another example. The length of a rectangle is 4 units, and its width is 3 units. The length of a second rectangle is 8 units, and its width is 3 units. Are the rectangles proportional? Let's write this out. 3/4 does not equal 3/8. Since the ratios of length to the width are not equivalent, the rectangles are not proportional. Now suppose you're driving a car at 75 miles per hour, heading to a destination that's 300 miles away. That is, for every hour that passes, you drive 75 miles. In this case, distance is directly proportional to hours, because as hours increase, distance also increases, and the rate of increase does not change. This table shows an increase of 75 miles for every 1 hour. The graph shows a straight line intersecting the origin. The equation is of the form y equals kx, where k is the constant of proportionality. Here, the constant of proportionality is 75. Every hour amount is multiplied by 75 to calculate distance. Now let's consider the same journey but with a different relationship. You travel the same 300 miles, but instead of traveling at 75 miles per hour, you travel at 60 miles per hour. How much longer does the trip take at the slower speed? From the previous example, we know that y equals 75 miles per hour times by 4 hours equals 300. Now you are driving slower. So you have y equals 60 times x, which represents the number of hours traveled, equals 300. So to solve for x, You divide by 60 on both sides and get x equals 5. Here, distance is inversely proportional to time because as time increases, distance to the destination decreases. You get closer every hour. The distance doesn't change, so the constant of proportionality is 300. What does change is the speed. The graph shows all possible speed-time combinations to drive the 300-mile distance. If you drive 300 miles per hour, it would take you 1 hour. Whereas if you drive 1 mile an hour, it would take you 300 hours. Equations showing inverse proportionality have the form y equals k over x, where k is, again, the constant of proportionality. Here, the distance 300 could be divided by the number of hours to calculate the speed, or it could be divided by the speed to calculate the number of hours. Suppose you drove to the same place again, and it took you 3.5 hours. How fast did you drive? Well, you've got y, which is your speed, is equal to k, your constant of proportionality, which is 300, divided by the total number of hours, 3.5, and that gives you that your speed is roughly 86 miles per hour. Now that we've covered proportions, let's talk about percentages. When we deal with percents, they can be treated like proportions. The word percent literally means per 100. So knowing that, we can figure out any relationship we need to. The key to percents is figuring out the whole and the part. Simply put, the whole is the quantity represented by 100%, and the part is the piece of the whole represented by some other percent. Generally, proportions with percents look like this. The whole amount over 100 is equal to the partial amount over the partial percent. Your restaurant bill comes to $33.75. You received exceptional service, so you want to leave a 20% tip. How much do you tip? Using a bar model can come in handy when visualizing these problems. For instance, $33.75 over 100 is equal to whatever your tip is going to be over 20. So if you look, we can do 33.75 over 100 divided by 5 over 5, and that gives you 6.75 over 20. Since the total amount is proportional to the tip amount, we can simply divide the total amount by 5 to arrive at the tip amount. Division by 5 also makes sense because 20 is 1/5 of 100. Suppose you went back to the restaurant and had a bill of $26.34, but decided to leave the typical 15% tip. How much do you leave? The bar model still helps us visualize. So we have 26.34 over 100 is equal to our tip amount over 15. This time, it's not as easy as dividing by 5, since 15 doesn't go evenly into 100. Here's a different way of using equations to think about it. If 26.34 is equal to 100%, then 0.2634 is equal to 1%. From there, we're going to multiply both sides by 15, and you get 3.941 is equal to 15%. Now we know you left about $3.95. You visit a store that's having a 25% off sale. You pick out some clothes and your total comes to $140.67. How much would full price have been, and how much did you save? With a 25% discount, that means you paid 75% of the full price. So you have your original price over 100, which is equal to 140.67 over 75. If 140.67
is equal to 75%. So if you divide both sides by 3, you get 46.89 is equal to 25%. And then if you multiply both sides by 4, you get 187.56 equals 100%. The original price was $187.56. So you saved $46.89. Suppose your friend went shopping with you and used a coupon for an extra 10% off. This coupon was calculated after the total was calculated, so it came off the sale price. What was the total discount percentage from the original price if your friend spent $211.89? So if you have $211.89 is equal to 90%, then if you divide both sides by 9, you get 23.54 is equal to 10%. From here, you would multiply both sides by 10 and get 235.4 equals 100%. So 100% of the sale price equals 75% of the original price. So we have $235.40 is equal to 75% of the original price. From here, if you divide each side by 3, you'll get $78.47 is equal to 25%. Then we'll multiply both sides by 4 to get $313.87 is equal to 100%. We can figure out a percentage by simply dividing the part by the whole and then multiplying by 100. In this case, the percentage paid is the amount paid over the original price times 100. So from the previous example, we have this. This is the percentage your friend paid. 100 minus 67.5 is equal to 32.5%, which is the total discount percentage your friend saved. You may have heard a math teacher or two say math is a language. If that is true, then algebraic rules and notation should be considered the grammar and punctuation of the language of math. Some students who struggle with math are confused by how to apply the rules and interpret the notation. In this video, we will focus on the notation and interpretation of exponents. This video will focus on the meaning of exponents that are natural numbers, also referred to as counting numbers, which are 1, 2, 3, things like that. Other types of exponents are interpreted differently and will be covered in other videos. Let's start by quickly reviewing some terminology. An exponent is written as a superscript on a number or algebraic expression, which is referred to as the base. There are a few ways to verbalize a power. This simple example can be read as 5 squared, 5 to the second, 5 raised to the second power, or 5 raised to the power of 2. In any case, the exponent should be interpreted as repeated multiplication. Whatever is defined as the base should be multiplied by itself however many times the exponent implies. For example, 5 squared equals 5 times 5. This can then easily be evaluated as 25. Let's look at some more examples. 7 cubed. This time the base is 7 and the exponent is 3. This can be read as 7 to the third or 7 cubed. Raising a base of 7 to the power of 3 means to multiply 7 by itself 3 times. 7 times itself 3 times equals 343. Let's try another one, but this one will look a little different. -2 squared. It is important to point out that parentheses are being used with this example to define the base. -2 is being raised to the second power. The interpretation is the same. Simply multiply -2 by itself twice. Multiplying two negative numbers using parentheses results in a positive value. But if we were to take the parentheses away and instead say -2 squared, then our answer would be -4. Why? Because the 2 is squared before the effects of the negative can take place. So we have 2 times 2 equals 4, and then the negative affects it. Let's try another one with negatives. -5 cubed. This is equal to -5 times -5 times -5, which gives you -125. Powers of 10 are used frequently in math and science applications. Scientific notation uses powers of 10 to express very large or small values in an efficient and organized manner, but we'll dive into that topic in another video. Exponents are also used to raise algebraic expressions to powers, but the meaning is the same. Multiply whatever the base is by itself, however many times that is indicated by the exponent. Here are a few examples. X cubed is equal to x times x times x. As you can see, the notation x cubed is a more efficient way to write the expanded version of x times x times x. 2x cubed is equal to 2 times x times x times x. Notice that the base here is x. Adding parentheses to an expression changes the meaning. If you put in parentheses, 2x cubed means 2x times 2x times 2x, which is equal to 2 times 2 times 2 times x times x times x, which when you simplify that, gives you 8x cubed. Let's try one more example before we go. X plus 2 squared. Once again, the parentheses here are used to define the base to be x plus 2. The exponent of 2 instructs you to multiply this base by itself twice. So it equals x plus 2 times x plus 2. Multiplying these two binomial expressions results in the quadratic expression x squared plus 4x plus 4. So, as long as you can identify the base, the multiplication of that base by itself becomes pretty straightforward. As mentioned, the interpretation of notation in math is half the battle. Practicing the basics is key in order to gain confidence for more complicated math content.
Now, I know what you're thinking. What does this phrase actually mean? Quite a bit, actually, because that saying provides the key to remembering an important math concept: the order of operations. The order of operations is one of the more critical mathematical concepts you'll learn because it dictates how we calculate problems. It gives us a template so that everyone solves math problems the same way. Let's start off with a simple question. What is an operation? An operation is a mathematical action. Addition, subtraction, multiplication, division, and calculating the root are all examples of a mathematical operation. Let's take a look at this problem. Looks easy, right? Well, it wouldn't be so easy if we didn't understand the order in which the math operation occurs. If we didn't have rules to determine what calculations we should make first, we'd come up with different answers. Should you start by subtracting 4 minus 6 and then multiplying by 7? No. The order of operations tells us how to solve a math problem. And this brings us back to Aunt Sally. Operations have a specific order, and this is what Please Excuse My Dear Aunt Sally helps us to understand. It's an acronym PEMDAS, or PEMDAS, that tells us in which order we should solve a mathematical problem. So first is please, which stands for parentheses. So we solve everything inside of the parentheses first. Then E, excuse, which is for exponents. We solve that after we solve everything in a parentheses. Multiplication, which is the my, and this happens from left to right. And then division, which is the dear, which also happens left to right. And then we have addition and subtraction, which also happens from left to right. And this is Aunt and Sally. Okay, so now that we know the order of operations, let's apply it to our problem that we have here and solve. So let's kind of go down our list. We don't have parentheses and we don't have exponents, but we do have multiplication. So we do that before we do any addition and subtraction. So let's go ahead and multiply 7 times 4. That gives us 28. And now we're subtracting 6, which gives us 22. Now let's look at another problem. Without the operations, you could calculate this as 7 plus 7, which is equal to 14, times 3, which is equal to 42. And this would be wrong. Remember, you multiply before you add. Therefore, the equation should look like this. So when we do problems like this, we can use parentheses to group together our numbers that are going to take place first. So in this case, it's 7 times 3. And when we do that, we get 21, and we have plus 7 left over. When we add those together, we get 28, and that's our answer. Let's look at some more complex problems. The order of operations dictates how to solve this problem. Remember, you multiply exponents first. Here's the wrong way to solve the problem. Why is that wrong? Because you violated the order of operations. You do not multiply first. You perform an operation on the exponent first. This is how it should be done. See, solving the equation in the right order provides the correct answer. Let's try out one more problem. This one is a little bit more challenging, but it perfectly illustrates the order of operations. Remember the order. What do we do first? The number inside the parentheses. So 8 times 6 is equal to 48. Then we subtract 15, and that gives us 33. Here's how the problem looks now. So our next step is multiplication and division. So let's perform all of our multiplication and division problems and then see what we have left. Now we finish with addition and subtraction. So here's what we have. And our answer is 37. There is an exception. If an equation only has one expression, you don't have to follow the order of operations. Here are some examples of single expressions. 10 plus 10. Well, there are no other operations, so you just know to go ahead and add them together and you get 20. Same thing with subtraction, multiplication, or division. All of those are single expressions.
To get started, let's quickly review what perimeter and area measure. Imagine we have a triangular-shaped yard. If we wanted to build a fence around our yard, we'd need to know the distance around the yard. This is the perimeter. If we wanted to buy sod for our yard so that we could have a lovely green space, we'd need to know the area of the yard so that we could buy the correct amount. And while it might be a bit unusual to have a yard that is the shape of a triangle, you might have part of a yard that you want to fence or sod shaped like a triangle. Okay, now that we know what perimeter and area are, let's figure out how to find the perimeter. We don't need any fancy formula or anything. All we need to do is add the length of the sides together. So if we know all the sides of our yard, we can easily find the perimeter. "20 meters plus 20 meters plus 12 meters gives you 52 meters of fence." Not much to that one. Notice that the answer is given in meters. That's because perimeter is a distance. Walking around the yard would mean walking 52 meters. That's all there is to it. No matter what type of triangle you have, just add up the length of the sides and you have your perimeter. Now let's deal with area. There is an actual formula for finding the area of a triangle. The formula is area equals 1/2 base times height. Let's quickly explain where that 1/2 comes from. The formula for the area of a parallelogram is area equals base times height. If we compare the two shapes, we can see that a parallelogram can be made by two equal-sized triangles. So we can say that a triangle is half a parallelogram, which is where the 1/2 comes from in the formula. For triangles, the formula for area does work a bit differently depending on the type of triangle. Let's start with right triangles. We have our formula, but the question we need to answer is which side is B and which side is H. For a right triangle like this one, B and H are the two sides adjacent or next to the right angle. It doesn't matter which is which, so let's say that B equals 6 centimeters and H equals 8 centimeters. Now we can plug them into our formula. It's always a good idea to substitute with parentheses to help keep things organized. We've even left the units in so that we can see what will happen with them. At this point, we only have multiplication left to do. So according to the commutative property of multiplication, we can rearrange before multiplying. Now let's solve this. Area equals 1/2 times 6, which is 3. 3 times 8 gives you 24. And centimeters times centimeters gives you centimeters squared. So we end up with our area as 24 centimeters squared. For area problems, the answer will always be in square units. That's because we're trying to determine how many square centimeters will fit in our triangle. We can see that clearly by looking at an isosceles right triangle that has legs measuring 5 units on some graph paper. How many squares will be inside the triangle? We can count them. First, we'll count the whole squares that fit inside, then we'll add the half squares. There are 10 full squares plus 5 half squares, for a total of 12.5 squares. If we use our formula, we'll find the same thing. Now we've seen the formula work and gained a better understanding of why the units are squared. All we have left to do is find the area of acute and obtuse triangles. Let's start with an acute triangle. Note that the height is always perpendicular to the base. From here, we can find the area. Here we have our area equals 1/2 times the base, which in this case is 12 centimeters, times the height, which is 8 centimeters. So we get 1/2 times 96 from 12 times 8, which gives us 48 centimeters squared. The same thing applies to obtuse triangles, except the height or altitude will often appear outside of the triangle, like this. We can see that the height of the triangle is 6 centimeters, and the side it is perpendicular to is the base, which measures 9 centimeters. We don't need the other two numbers at all, so let's plug in the base and the height. That's all there is to it. Here's one more for you to solve on your own. Try pausing this video and then finding the perimeter and area of this triangle. Think you got it? The perimeter is 34 meters and the area is 49 meters squared. Hello, and welcome to this video about line graphs. Today we'll explore what a line graph is and what type of data it's used to represent. We'll also learn how to use line graphs to interpret situations in the real world. Before we get started, let's review a few things. First, a graph is a diagram that shows the relationship between two quantities, which we call variables. These variables are measured along the x-axis and y-axis on a coordinate plane. A line graph is a type of graph that displays quantitative data as a series of points called markers or data points. These data points are connected by straight line segments. The connected data points show the relationship between two variables. A line graph is typically used to show information that changes over time. Let's take a look at an example. This line graph shows the change in a company's profits over several years. The x-axis is labeled year and the y-axis is labeled profits. We see that line segments connect the data points plotted on the graph. Since the line segments are generally moving in a positive direction, we can say that the company's profits tended to increase from 2006 to 2013. Let's take a look at the line segment connecting the data points for the years 2009 and 2010. We can see that this particular line segment is positioned in a downward or negative direction. This tells us that the company's profits decreased from 2009 to 2010. What do you notice about the line segment connecting the data points for 2012 and 2013? They form a straight horizontal line. This shows that the company's profits neither increased nor decreased during this time frame. Instead, they stayed the same. When constructing a line graph on a coordinate plane, the x-axis is always used to plot the independent variable, and the y-axis is always used to plot the dependent variable. With line graphs, the independent variable is usually time. In the graph we just looked at, the independent variable is years, which is a measurement of time. The dependent variable is the factor that changes over time. In our example, the dependent variable is the company's profits, which increased and decreased from 2006 to 2013. Line graphs are an important part of our everyday lives because they can swiftly communicate data and trends. They're used in a wide variety of fields, including sales and marketing, science, psychology, economics, and business. Additionally, line graphs can be used to make predictions. Let's look once more at our line graph showing the company's change in profits. Based on the general trend shown, do you think the profits will increase or decrease in the future? We can infer that the profits may continue to increase based on the positive trend shown in previous years. Let's look at another line graph together. This graph shows how much time Dave spent playing video games each day. The horizontal x-axis shows the independent variable, which is days, and the vertical y-axis shows the dependent variable, which is minutes spent playing games. Each marker shows the data point for how many minutes of video games Dave plays each day. Let's use this information to answer some questions. Which day did Dave spend the most time playing video games? Dave spent the most time playing video games on day 4. We know this because the marker for day 4 is higher than the markers for the rest of the days shown. On day 4, Dave played games for 100 minutes. That's a lot of gaming. What is the difference in the amount of time Dave spent playing video games on day 2 and day 6? Looking at the markers, the graph shows that Dave played games for 70 minutes on day 2 and 90 minutes on day 6. The difference is calculated by subtracting. Since 90 minus 70 equals 20, the difference is 20 minutes. Dave spent 20 more minutes playing video games on day 6. How many minutes did Dave play video games altogether? To find the total amount of time Dave played video games, add the amount of minutes played each day. 30 plus 70 plus 60 plus 100 plus 10 plus 90 equals 360. Therefore, Dave spent 360 minutes playing games from day 1 through day 6. A line graph can show multiple sets of data if the same two variables are related. Graphing multiple data sets on a line graph can be very informative because they can be compared and contrasted. When this happens, each data set is typically represented by a distinct color. The line graph contains a key that explains what data set each color stands for. Let's take a look at a line graph that shows two sets of data. This graph shows how much money was raised in a school fundraiser each month. The horizontal x-axis shows the independent variable, which is month, and the vertical y-axis shows the dependent variable, which is amount raised. Each marker shows the data point for how much money was raised in each month shown. The two data sets are graphed in two different colors, blue and green. By reading the key beneath the graph, we see that green represents money raised by 7th grade students, and blue represents money raised by 8th grade students. Let's use this information to answer some questions. Pause the video after each question is asked. Then look at the graph and see if you can answer it yourself. When you're ready, resume and check your work. Which grade raised more money in September? 8th grade students raised more money than 7th grade students in September. Remember that blue data points represent 8th grade students and green data points represent 7th grade students. Looking at the markers for September, we see that the blue marker is higher than the green marker, so 8th grade students raised more money in September. Which grade raised more money in the months of June and August combined? The 8th grade students, shown in blue, raised $60 in June and $60 in August. 60 plus 60 equals 120, so the 8th grade students raised $120 in June and August. The 7th grade students, shown in green, raised $20 in June and $100 in August. 20 plus 100 equals 120. So the 7th grade students raised $120 in June and August. As you can see, both grades raised the same amount of money in the months of June and August combined. In which month did 8th grade students raise the smallest amount of money? How much money was raised? We can find the answer by examining the blue markers representing the 8th grade data points in each month. The month that the marker is placed the lowest is in May, when they raised $40. I have one last graph for you to analyze. This one is a little more challenging, but I know you can handle it. As you can see, this line graph displays 3 sets of data. Consider the following questions. Which variable is independent? Which is dependent? Explain. In which month was the number of computers sold in shop C almost identical to the number sold in shop B? In which months did shop A sell more computers than shops B or C? Pause this video and analyze the line graph, and see if you can answer these questions yourself. When you're ready, resume the video and we'll go over the answers together. Now that you've tried these problems yourself, let's go over them together. Which variable is independent? Which is dependent? Explain. The independent variable is months, which is on the x-axis. The independent variable is always measured along the x-axis, and it usually pertains to time. In this case, time is measured in months. The dependent variable is number of computers sold, which is on the y-axis. The value of the dependent variable relies on the independent variable. In this case, the number of computers each store sold depends on the month. In which month was the number of computers sold in shop C almost identical to the number sold in shop B? March. When we look at the markers for that month, we see that the red marker for shop B and the green marker for shop C almost overlap entirely. This indicates that the number of computers sold by each shop was about the same. In which months did shop A sell more computers than shops B or C? February and March. To find out when shop A sold the most, look for when the blue markers are higher than the green or red markers. Shop A sold 40 computers in February and 50 computers in March. Line graphs are useful tools for showing how factors change over time. Hi, and welcome to this overview of quadratic equations. Before we dive into how to solve them, let's first talk about quadratic functions. When we graph quadratic functions, we'll notice that they can be used to tell all kinds of visual stories, from a daredevil shooting out of a cannon to a satellite dish listening to interstellar signals. Equations for these functions generally look like this. F of x, or sometimes y, equals ax squared plus bx plus c. And their graphs form a characteristic shape called a parabola, which looks something like this one. The different characteristics of quadratic functions that are most commonly analyzed are the vertex, which is the maximum or minimum value, the x-intercepts, which are also known as the zeros, and the axis of symmetry. Now that we have a little background, let's dive further into solving quadratic equations and interpreting the results. So what do we mean by solving? In this case, one of the things it means is to figure out which values of the variable, if any, make the equation 0. So instead of the function f of x equals ax squared plus bx plus c, we write the related equation. 0 equals ax squared plus bx plus c. In other words, the solutions to a quadratic equation are the values that make the quadratic function true when f of x, or y, is equal to 0. This is the function f of x equals negative x squared plus 2x plus 8. Every point on the graph satisfies this equation. Solving 0 equals negative x squared plus 2x plus 8 gives us two solutions because the function equals 0 only when it crosses the x-axis. Here's another way to look at it. To solve a quadratic equation means to find the x-intercepts of the related function, also known as the zeros. Before you get started with any solving method, make sure your equation is written in standard form. ax squared plus bx plus c equals 0. This will prevent errors and can provide insight into choosing the most appropriate method for solving an equation. If your equation is not in standard form, simply add or subtract terms as needed. For instance, 2x plus 8 equals x squared is not written in standard form, but by subtracting x squared from both sides, we get negative x squared plus 2x plus 8 equals 0. Which is now in standard form. The first method we'll look at is graphing. If you have access to a graph or can easily create one using the internet or a graphing calculator, this can be a great method to use. Let's look at an example. Here is the graph of f of x equals negative x squared plus 2x plus 8. The solutions to the equation negative x squared plus 2x plus 8 equals 0 are x equals negative 2 and x equals 4. Solutions can always be verified by plugging them back into the original equation. Sometimes, quadratic equations can be simplified and solved by factoring. Looking at our sample equation, we have negative x squared plus 2x plus 8 equals 0. The left side can be factored into negative x plus 4 times x plus 2 equals 0. Now let's pause. There's a property called the zero product property that says that if there are two numbers whose product is 0, one of the numbers must be 0. In more mathematical terms, if a and b are real numbers and a times b equals 0, then a equals 0 or b equals 0. Makes sense, right? Back to our equation. Negative x plus 4 times x plus 2 equals 0. Means that negative x plus 4 equals 0, or x plus 2 equals 0. So we solve both. We're going to subtract 4 from both sides, which gives us negative x equals negative 4, and then divide by negative 1. We get x equals 4. For this equation, we subtract 2 from both sides, and we're left with x equals negative 2. So our zeros are x equals 4 and x equals negative 2. These match what we found on our graph. Factoring is nice, but not every equation can be factored easily. Luckily, there are a couple more methods we can use, including the completing the square method. The idea behind this method is to create a quadratic equation that contains a perfect square, and then take the square root to find the solutions. Here's our equation again. Negative x squared plus 2x plus 8 equals 0. To complete the square, the equation needs to not only be in standard form, but the coefficient on the squared term needs to be positive instead of negative. So we divide all terms by negative 1 to get ready. This gives us x squared minus 2x minus 8 equals 0. First, move the constant term to the other side by itself. For this, we'll add 8 to both sides. This gives us x squared minus 2x equals 8. Pause. Now we need to add a number that creates a perfect square on the left-hand side. Let's consider some perfect squares. To complete the square in our equation, we'll need to add a number to both sides of our equation. In the examples, notice that the number is b over 2 squared. 4 equals 4 over 2 squared, 9 equals negative 6 over 2 squared, and 16 equals 8 over 2 squared. In our equation, we'll add negative 2 over 2 squared, which equals 1, since our b is equal to negative 2. Remember, an equation only stays equal if you change both sides in the same way. So since we're going to add 1 to our left side, we also need to be sure to add 1 to the right side. Now the left side can be factored. X minus 1 squared is equal to 9. Since we have a perfect square, we take the square root of both sides. On the right-hand side, we need to account for both positive and negative square roots. Now we'll split into separate mini-equations. X minus 1 equals 3, and x minus 1 equals negative 3. We're going to solve for x over here by adding 1 to both sides, which gives us x equals 4. And here we're going to do the same, add 1 to both sides, which gives us x equals negative 2. We get the same solutions as before. Completing the square can be used with any quadratic equation, but if you start with a perfect square and don't realize it, the equation will look the same after you use this method as it did when you started. There is one last method for us to examine. The quadratic formula, as you'll see, involves the most algebra, but it has two distinct characteristics. One, it can truly be used with any quadratic equation, and two, part of it can be used to determine how many solutions to expect beforehand. Here it is in all its glory. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. The piece of the quadratic formula under the radical, the square root sign, is called the discriminant. Calculating its value helps us know how many solutions to expect. Let's take a minute to consider how many times a quadratic function can possibly intersect the x-axis. This example shows twice. Sometimes it's only the vertex, and sometimes not at all. Because of the shape, these are our only choices. In order for a graph like this to intersect the x-axis more than 2 times, it would need to change direction again and thus no longer be a parabola. Now let's consider square roots in general. If the square root of a number is greater than 0, there are 2 real solutions. Taking the square root of a positive number yields positive and negative roots. If the square root is 0, there is one real solution, 0. Taking the square root of 0 is 0. If the square root of a number is less than 0, there are 0 real solutions. We can't take the square root of a negative number and end up with a real number. So what does this have to do with the discriminant? If b squared minus 4ac is greater than 0, then there are 2 real solutions, 2 x-intercepts. If b squared minus 4ac equals 0, there is one real solution. The vertex of the parabola is the x-intercept. And if b squared minus 4ac is less than 0, there are no real solutions, no x-intercepts. Using our ongoing example, negative x squared plus 2x plus 8 equals 0, a equals negative 1, b equals 2, and c equals 8. The discriminant d is b squared minus 4ac, which is 2 squared minus 4 times negative 1 times 8, which is equal to 4 plus 32, which is equal to 36. Since 36 is greater than 0, we know that there are 2 real solutions to our equation, as expected. What's the point of calculating the discriminant? If you get in the habit of checking it every time, a few things happen. If there are no solutions to your equation, you'll know right away and can stop. If there are 1 or 2 solutions, the discriminant will serve as a check, regardless of the method used. If you use the quadratic formula, a chunk of it is already calculated. Speaking of the quadratic formula, let's try it out. Again, a is equal to negative 1, b is equal to 2, and c is equal to 8. Plus, we already know the discriminant. So we have negative b, which is negative 2, plus or minus the square root of the discriminant, which we found was 36, so the square root of 36, all over 2 times our a, which is negative 1. This is equal to negative 2 plus or minus 6 over negative 2. Now we're going to split it into 2 equations. We have negative 2 plus or 6 over negative 2, and negative 2 minus 6 over negative 2. This one is equal to 4 over negative 2, which is negative 2. This one gives us negative 8 over negative 2, which is equal to 4. So x equals negative 2 and x equals 4. We've seen all 4 quadratic equation solving methods in action. Now let's put some context around our practice equation. Suppose our function f of x equals negative x squared plus 2x plus 8 represents the height of a rock from the ground in meters you throw off of a small cliff as a function of time in seconds. We want to know how long it takes for the rock to hit the ground. In order to do that, we would solve the equation negative x squared plus 2x plus 8 equals 0, which we have already done many times over. Remember, the 0 represents 0 height. In function terms, this means on the x-axis. In this situation, that means on the ground. We know that our mathematical solutions are x equals -2 and x equals 4. In this situation, the solution of -2 doesn't make sense. What does it mean? 2 seconds ago? Travel back in time 2 seconds? We would state that the rock landed after 4 seconds. I hope this video helped you understand quadratic equations and how they work. Thanks for watching, and happy studying.